Hello friends, I Deepak Prajapati welcome you in lecture number 9 on Lagrange method for solving first order quasi-linear partial differential equations. Today we are going to discuss the last type of solving Lagrange auxiliary equations. So in this last type we will consider those type of problems in which we are not able to find out multipliers P1, Q1, R1 such that we obtain 0 in the denominator as we have seen in the last lecture. So in those type of equations we will try to generate new fractions by selecting multipliers P1, Q1, R1 such that the numerator in the new generated fraction is exact differential of the denominator, and that generated fraction can be combined with one of the three fractions of equation 1. In some cases we can generate another new fraction by selecting appropriate multipliers, and then we can combine the generated new fractions to find out the solution of Lagrange auxiliary equations. So here we have written, if we take multipliers P1, Q1, R1, then each ratio of 1 is equal to P1 dx plus Q1 dy plus R1 dz divided by P1 into P plus Q1 into Q plus R1 into R. Now if the numerator of 2 means this one, P1 dx plus Q1 dy plus R1 dz, if this one is exact differential of denominator, that is P1 into P plus Q1 into Q plus R1 into R, then this new generated fraction can be combined with a suitable fraction in Lagrange auxiliary equations to give an integral. However, in some problems another set of multipliers P2, Q2, R2 say are so chosen that the fraction P2 dx plus Q2 dy plus R2 dz divided by P2P plus Q2 into Q plus R2 into R is such that its numerator is exact differential of the denominator. So this is another fraction which is generated using multipliers P2, Q2, R2 such that this numerator is exact differential of this denominator. That means this numerator can be written as differential of P2 into P plus Q2 into Q plus R2 into R. Okay, so this is nothing but the differential of the denominator P2 into P plus Q2 into Q plus R2 into R. So in fractions 2 and 3 we have the same thing, numerator is exact differential of the denominator. So we can combine fractions 2 and 3 to find out the integral. So we understand this with the help of example. As usual, this is Lagrange quasi-linear equation. So we try to solve it starting with Lagrange auxiliary equations. So Lagrange auxiliary equations are dx divided by y plus z equal to dy divided by z plus x equal to dz divided by x plus y. Now to solve these auxiliary equations, if you observe, we cannot apply any of earlier three types. So what we can do is we will generate new fraction such that the numerator is exact differential of the denominator. So you can see here we have z in these two terms. So if we take difference of these two fractions, z will cancel out. and if we don't require this last fraction, we can multiply it with 0. So this suggests to take multipliers 1, minus 1, 0. So choosing 1, minus 1, 0 as multipliers, each fraction of 1 equals, so 1 into dx plus minus 1 into dy, that is dx minus dy. Here y plus z minus of z plus x, that is minus z minus x. So z will cancel out, and this we rewrite as differential of x minus y, and here we have y minus x. So we can write y minus x as negative of x minus y, and here we have derivative of x minus y. So this is the new generated fraction in which this numerator d of x minus y is exact differential of the denominator x minus y. But we are not able to combine this new generated fraction 2 with any of these three fractions. So what we can do is we can generate another fraction. So as we have done in this case, now we can combine fractions 2 and 3. So we see here we have dy and dz, and we don't require x, so we can take difference of dy and dz. So I have to multiply this second fraction by 1, last fraction by minus 1, and I don't require first fraction, so I multiply it by 0. So another set of multipliers is choosing 0, 1, minus 1 as multipliers, each fraction of 1 equals, so now we have dy minus dz, 1 into dy minus 1 into dz, and we have z plus x minus x plus y. Minus x plus y, that will be minus x minus y, and this we can rewrite as x will cancel out, and we have z minus y, that I rewrite as negative of y minus z, and dy minus dz can be written as d of y minus z. So this is suppose third fraction. So here also numerator is exact differential of the denominator. Similarly we can combine last and first fraction, so we don't require this, and in last and third fractions differentials are dx and dz. So if we take the difference of y plus z and x plus y, y will cancel out. So we will select multipliers as 1, 0 and minus 1. So choosing 1, 0, minus 1 as multipliers, each fraction of 1 equals dx into 1, 0 into dy minus 1 into dz. So it is dx minus dz, and we have to take y plus z minus x plus y. So y plus z minus x plus y, that is minus x minus y. So y will cancel out, and dx minus dz can be written as differential of x minus z, and if we take negative sign outside, we can write this as x minus z. So we give this number 4. So we have generated 3 new fractions, and in each fraction numerator is exact differential of denominator. So using these 3 fractions, we can find out the 2 integrals of Lagrange Auxiliary Equations. So suppose we combine fractions number 2 and say 3. So first we take fractions 2 and 3. Taking fractions 2 and 3, so we have d of x minus y divided by x minus y, and here we have y minus z. Negative sign will cancel out. So I directly write by cancelling negative sign. Here I have d of x minus y divided by x minus y, and fraction number 3 is y minus z. So differential of y minus z divided by y minus z. So if we integrate, we get integral of d of x minus y divided by x minus y is log of x minus y. This is log of y minus z, and constant of integration can be adjusted as log c1. So this we can rewrite as log of x minus y minus log of y minus z equal to log of c1. So therefore log of x minus y divided by y minus z equal to log c1 using the property of logarithm. And because log is 1 function, this implies x minus y divided by y minus z equal to c1. So therefore first integral is u equal to x minus y divided by y minus z, which is c1. Similarly, we can combine fractions 3 and 4 or fractions 2 and 4. So suppose we combine fractions 3 and 4. So taking fractions 3 and 4, we get, in fraction 3 we have d of y minus z divided by y minus z, and negative sign will cancel out because we have d of y minus z divided by y minus z, negative sign, and here d of x minus z divided by x minus z, negative sign will cancel out. D of x minus z divided by x minus z. So integrating, we get integral of d of y minus z divided by y minus z is log of y minus z. And right hand side integral will be log of x minus z, and suppose we adjust constant as log c2. So therefore log of y minus z minus log of x minus z equal to log C2. Therefore ln y minus z divided by x minus z equal to log C2. And using property of logarithm, log function is 1 function, y minus z upon x minus z is C2. So this is the second integral. Therefore v equal to y minus z divided by x minus z divided by equal to C2. So this is the second integral of Lagrange Auxiliary Equations. Now if you wish, you can compare fractions 2 and 3 also, x minus y upon x minus y, x minus z upon x minus z. So if you have compared fractions 2 and 4, you would have obtained x minus y upon x minus z equal to C2. So this is also valid solution, but be careful, you have to write only 2 integrals for Lagrange Auxiliary Equations. So instead of taking 3 and 4, suppose you are taking 2 and 4, then you will obtain this integral. So that is also correct, but we have to write down only 2 solutions in Lagrange Quasilinear Equations. So now we have obtained u and v, so we are able to write down general solution. Therefore the general solution is arbitrary function of uv, say phi, equal to 0. So therefore phi of u is so we have obtained u equal to x minus y upon y minus z. Divided by y minus z, comma v is y minus z divided by x minus z. Equal to 0, where phi is an arbitrary function. So in this way we can use this method of generating new fractions such that numerator is exact differential of the denominator, and using this idea we can solve the Lagrange Quasilinear equation. So we consider one more problem of this type. So given equation is Lagrange Quasilinear equation. So we start with Lagrange Auxiliary Equations. So they are dx divided by y square into x minus y, dy divided by coefficient of small q, which is x square into y minus x, equal to dz divided by z into x square plus y square. Now if you observe here, we can combine fractions 1 and 3. So because we have differentials are dx and dy, and remaining terms are in terms of x and y only, so we consider or we combine first two fractions. Okay, so it is possible to compare first two fractions of 1. So taking first two fractions of 1, we have dx divided by y square into x minus y equal to dy. Here I write y minus x as negative of x minus y. So x minus y will cancel out, and we take this x square with dx, and this is equal to minus y square dy. So therefore x square dx plus y square dy equal to 0. So this is separable. So integrating, we obtain x cube by 3 plus y cube by 3 equal to, say, c1 by 3. So therefore x cube plus y cube equal to c1. So therefore u equal to x cube plus y cube equal to c1. Now to find out second integral, we again concentrate on Lagrange Auxiliary Equations. So here if we combine again, we have everything in terms of x and y in fractions 1 and 2. Now if we take a difference of 1 and 2, then if I write this as, or if I multiply this by minus 1, then I will have x square into x minus y, and if I multiply this by 1, so I have y square into x minus y plus x square into x minus y. I take minus 1 in the multiplication of this, and that will become x minus y. So if we will take x minus y common, we will have x square plus y square. So we will be able to combine that new fraction with this last fraction, because we will be able to cancel out x square plus y square. So we are generating new fraction by taking multipliers 1 minus 1, and because we don't require this, we take third multiplier as 0. So we take multipliers 1 minus 1 and 0. Taking 1 minus 1, 0 as multipliers, each fraction of 1 equal to so we will have dx minus dy, and this is multiplied with 1, so we write y square into x minus as it is multiplied with 1, so it is y square into x minus y, and this is multiplied with minus 1, so we take minus 1 in the multiplication of y minus x, and we will obtain x minus y. So after multiplying with minus 1, we will write x square into x minus y. So plus x square into x minus y, and dx minus dy is nothing but differential of x minus y, and if we take x minus y common, we are left with y square plus x square. So this is the new generated fraction. We give it number 2. Now if we observe given equations, Lagrange Auxiliary Equations, then in last term we have dz upon z into x square plus y square. So that I can combine with this new generated fraction, because we have x square plus y square, that will cancel out with this last fraction if we compare them. So here we will have dz upon z, and in that fraction we will have d of x minus y divided by x minus y. So we take fraction number 2 with last fraction of 1, taking fraction 2 with last fraction of 1, we get, so fraction 2 is d of x minus y divided by x minus y into x square plus y square, and last fraction of equation 1 is dz upon z into x square plus y square. So here we write dz upon z into x square plus y square. So therefore d of x minus y divided by x minus y equal to dz upon z. So this is separable, and we can easily find out its integral by taking integration. Integrating, we get log of x minus y equal to integral of 1 by z is log z, so ln z plus ln c2. Therefore ln x minus y minus ln z equal to ln c2, and using property of logarithm we have log of x minus y divided by z equal to log c2, and therefore because log is 1 function, this is x minus y upon z equal to c2, and therefore the second function is v equal to x minus y upon z equal to c2, and finally therefore the general solution or integral is phi of arbitrary functions u and v equal to 0. Therefore u is, what is our u? So u is x cube plus y cube, so we put u equal to x cube plus y cube, and v have just obtained, v is x minus y divided by z. Equal to 0, where phi is an arbitrary function. So this is all about type 4 of solving Lagrange Quasilinear equation. So I hope you like this lecture. Thank you very much.